Good afternoon. We continue with our lecture which was looking at behavior of masonry under compression, and we examined the effect of slenderness ratio and the effect of eccentricity ratio, and how we account for these two important geometrical second order effects in reducing the compression capacity of a masonry wall. So, that is what we were looking at in the last class. Of course, the vertical load carrying capacity of a masonry wall is also affected by other factors. We had briefly looked at some of these factors at the beginning of this module, and we will examine this a little closely today before we move on to behavior and bending itself. So, we were looking at how codes represent, and that is where we concluded in our last lecture, how a code would give you design curves that you can use for estimating the dimensions for a given wall or the design loads for a given combination of geometry and eccentricity of loading. So, we did see how the IS code 1905 looks at stress reduction factor as a function of what the eccentricity ratio E by T, with T as the wall thickness and H by T was, and we saw those curves. And I did mention to you in the last lecture that we make our calculations for the adopted approach based on linear elastic analysis, linear elastic behavior of the material. Now, that is going to be conservative, and across the world different codes adopt different approaches. One of the aspects that can see a difference in the way these curves are presented in different codes is if a nonlinear stress strain relationship has been used for the masonry compression behavior. Then you will see that you get a more accurate estimate of the second order effects. So, I am just looking at some other forms in which you will see design curves made available for masonry design. So, in this particular example that we are seeing, you can see the load, normalized load on the y axis, P, the elastic buckling load to the P critical, and on the x axis you have the total deflection. It includes the eccentricity of the load itself. So, you have yc, which is the mid height displacement that you would get in a pin-pinned wall, plus the eccentricity of the load itself normalized to the thickness of the wall given as d here. So, in this set of curves that you see, if we were to consider the column to behave in an elastic manner even at ultimate and provide the material with tensile resistance, then the load deflection curves beyond the point where the continuous lines start reducing. If it were assuming fully elastic condition, you will have you would actually follow those dotted lines there. So, this is another way of representing the P by P critical to the eccentricity ratio, and this is from work quite a few years ago. Now, one aspect that you need to keep in mind is it has been observed, and most of the analytical forms, most of the design graphs would account for this aspect, for this phenomenon, that when the sum of the mid height deflection, the maximum mid height deflection that you get in the wall because of the second order effect, and the initial eccentricity that is there because of the eccentricity of the load. So, in this case we are looking at yc as the mid height deflection, and EP is the eccentricity of the load. So, when this reaches 1/2 of the section thickness. So, when YC plus EP by D in this case is equal to 0.5, then you typically get loss of stability. Collapse is observed at this limit, and most codes would put a cap beyond this particular value. So, you can see again that at E by D, that is total eccentricity plus the mid height deflection reaches 0.5, you have a reduction in the capacity coming right down to 0. Now, if the dotted lines here imply that there is no inelasticity in the cross section and there is tensile resistance available in the cross section. So, in that case resistance is still there, but in reality you are looking at very low tensile resistance and plastification. So, once you assume plastification of the section and you assume that there is no tensile resistance, crack formation and subsequent plastification of the cross section is occurring, which is what is causing the reduction in the load carrying capacity. The stress reduction factor itself, we have seen how with H by T greater than 25, these are governed by buckling, but less than 25 and less than 25, you start seeing that you can have crushing in the cross section that can occur before the instability due to buckling occurs itself. So, typically the stress reduction factors that we saw for IS 1905, we will compare that in a moment, but this is the other way in which you would see codes giving you stress reduction factors that you should be using to account for second order effects, again as a function of H by D, and you would use different values for different eccentricity ratios as you can see. So, at about 25 at H by T of 25, which is the red dotted line with no eccentricity of the load itself, you do not use a stress reduction factor. So, you can see that at H by D of 25, the stress reduction factor with no eccentricity of the load is 1. So, there is no reduction that is required, and this comes from observations that beyond H by T of 25 is when failure due to buckling is expected to occur. So, this is what we had seen, and in the IS code we have the values that go up to H by T of about 27, and we do see some differences, but more or less this is what is how codes would represent the effect of second order geometrical aspects such as H by T and E by T. Okay. Now, as I had mentioned earlier, there are other factors that will come into the picture, and these phenomena, particularly the interaction of the wall with the floor slabs and the rotation at that junction, has an important role to play. It actually changes the boundary conditions and would alter the vertical load carrying capacity of the wall itself. So, that is an aspect that I would like to look at. Now, if you were to make an estimate, an accurate estimate of the effect of second order P delta in the load carrying wall, you need to consider the fact that beyond the compressive strength of the material, you are going to have plastification of the section, and that needs to be considered. Finite resistance of the material in compression needs to be considered. You can consider a nonlinear constitutive relationship to get a more accurate estimate of the P delta Fx, and the time varying deformations can also be considered. Your load configuration is going to change because of the deformation itself, and these could also be considered to get a more accurate estimate itself. But boundary conditions getting affected is something that you need to keep in mind and can be accounted for in arriving at the vertical load carrying capacity of the wall itself. So, let's examine how the interaction between the wall and the slab is, and if one were to be accounting for wall slab interactions in the vertical load carrying capacity of the wall, what sort of a framework could you use for this calculation itself. So, the floor slab induces a restraining effect on the wall when the wall is subjected to bending due to the gravity forces acting eccentrically, or even when you have lateral forces acting on the wall. The role of the floor slab is it basically restrains the deformations in the wall. So, this slab has a restraining effect, and it is essential therefore to be able to understand what is this restraint offered by the slab, and can this restraint actually be considered in the vertical load carrying capacity of the wall itself. It influences the strength of the wall, both particularly in terms of the end rotations and what the actual eccentricity of the load is on the wall itself. So, we need to, in order to be able to arrive at an analytical form, let us look at the deflected shape and then the eccentricity of the loading to then use them within an analytical expression itself. Now, as we were discussing earlier, the problem that we looked at and arrived at an analytical closed form solution had first order eccentricity. We assumed that the top and the bottom eccentricities were equal, but you need not have that sort of a situation. You might have first different eccentricity at the top and the bottom, and this can come from changed boundary conditions at the top and the bottom. So, the top and bottom end conditions need not necessarily be same, we idealize it as the same. So, as I said, the first assumption that we have a hinge at the top and the bottom itself is based on a certain set of conditions of crack formation at the interface with the adjacent material. Now, this could be a situation that has not occurred, so your top and bottom boundary conditions could be different itself. So, let us examine a few cases where you might want to make assumptions that are as appropriate as possible with respect to physical reality. If you were to consider a continuous reinforced concrete slab as the floor slab or the roof slab, and let us assume that this reinforced concrete slab is embedded into the wall thickness. If wall thickness is T, then we are assuming that the slab itself is embedded at least up to 2/3 of the wall thickness. And now, if the average compression at the interface between the slab and the masonry wall, the bearing stresses are of the order of 0.3 megapascals, 0.3 Newton per millimeter square, that can be assumed to give fixity. So, if you can make a quick estimate of what is the bearing stress at that interface, if you have embedment plus a bearing stress of the order of 0.3 MPa or higher, assuming that the joint is fixed is a reasonable estimate. You might have a situation which is different from this. If you have a flexible diaphragm, if you have a flexible floor, then the situation definitely changes. Now, let us look at if you have a timber floor, which is a flexible floor, or it could be the reinforced concrete slab that we examined earlier, but now let us say you do not have a bearing stress level of the order of 0.3 MPa, it is significantly low. In such a situation, the flexible floor, the timber floor, or reinforced concrete slab which has very little bearing stress, significantly low bearing stress, is not going to restrain the joint, and assuming that the wall is hinged is a reasonable estimate. Plus, the other aspect that you need to know is this is not just typology construction, the structural typology specific within the same building. As you go to higher floors, the stress levels in the axial force levels are going to be different, and therefore, the stress levels can also be different in the higher floors compared to the lower floors, and so you might not have the bearing stresses that we are talking of, a thumb rule of 0.3 MPa in the higher reaches of the building compared to the lower floors. So, this is something to be considered. If there is good bonding, then the out of plane deformations, the wall with its return walls, if there is good bonding, then the return walls are going to be acting as stiffeners, and you would be able to get a further contribution as far as lateral restraint is concerned. So, you are examining the wall and it is under axial forces, but now if the return walls are well bonded to the wall under examination, there is an additional resistance that is available to this deformation by the return walls, and it depends on how well the wall is bonded to the return walls. It is then it depends on if you want to consider this effect and whether the effect is actually having a significant role to play in the vertical load carrying capacity of the wall. Okay. So, if you are able to make an estimate of the end rotations, can that be brought in analytically? Yes, and this has been done. You need a certain amount of idealization, a set of parametric curves, as you can see in this graph here, have been created based on analytical formulations which link a certain set of conditions, the end rotations of the wall. You should be able to make an estimate of the end rotations of the wall, the load that is being applied to the wall, and the eccentricity of the load itself. So, these set of parametric curves from this work that is being quoted here, Salin 71, looks at being able to estimate the stress in the wall, the stress level in the wall, because of a combination of these effects, the end rotation of the wall, the total applied load, and the eccentricity of the load itself. Here let me make specific reference to the small figure that is there. Lambda h is the height of the element that you are considering. It is the height of the load bearing wall, of the load bearing element from a floor to the nearest inflection point. So, the point of zero moment. So, it depends on what sort of an idealization of the boundary condition have you made, and if h is the total height of the wall, and then depending on the deflected shape of the wall between the points of zero moment, you have lambda h. D is the total wall thickness, and B is the width of the cross section that is being considered, and sigma edge is nothing but the edge compression. We have been using FC in our earlier lectures, and that edge compressive stress is what is given in this graph as sigma edge. So, these curves are actually curves of constant edge stress. You have constant edge stress curves superimposed on these, on the other curves here. So, depending on the level of rotation that you have, the end rotations that you have, the end rotations are an estimate of the end rotations are given on the y axis. You can see that the rotations are here, the end rotations are here in terms of lambda h by d into phi v, which is an estimate of how much of rotation do you have in the wall itself. And then on the x axis you have lambda square h square by EI, E of the masonry, and I again the second moment of area of the cross section. And the second set of curves that you see here are curves of constant edge stress, and that is lambda square h square by EI multiplied by the area of cross section B into D into the edge stress. So, the second set of curves that you see are curves of constant edge stress, and they are superposed on this, and the curves are calculated for different levels of eccentricity ratio. So, each curve is for E by D of 0.083 and keeps increasing to about 0.5. And as we said, you will see that this E by D of 0.5 or E by T of 0.5 is a limiting value in most codes. So, this is if for a given load the maximum stress in a wall can be known if you can make an estimate of the end rotations and you know the eccentricity of the load. So, if you want to limit the maximum compressive stress in the wall, let us say you are working within a permissible stresses approach, then you know what is the maximum permissible stress that is allowed in the for the combination of materials that you are looking at. In this you will be through this sort of a graph, you will be able to check if for a given load and selected end rotations and eccentricity, would you be able to satisfy the requirements of the allowable stress itself. So, this is another useful form in which the effect of eccentricity, effect of the end rotations have been captured in parametric design curves. Okay. This is a work that has actually seen a lot of research. This is an area that has seen a lot of research. So, there are different ways in which this has been accounted for. So, if you are looking at a wall which is carrying your vertical load and sitting between floor slabs, and if the rotation, the end rotations are designated as phi and E being the eccentricity of the axial load P for a wall of height h. There are some other forms that have been developed. In this particular work, you can see that the deflected shape, now the deflected shape of the column has been idealized as being close to a parabolic deflected shape, and with that assumption you get an analytical form that you can use. And in this particular situation, in this particular example, if the angle of rotation at the ends is estimated, right, if you can make an estimate of the angle of rotation at the ends, the bearing capacity, the failure mode, that is in what way is the wall slab interaction expected to fail, and the eccentricity and the end moments can be arrived at. So, in terms of mode of failure, you can either have failure in the section due to the compressive strength of the material being reached, or you could have failure due to buckling, and that depends on the H by T ratios that you are looking at and the relative strengths that is being examined. You can have the entire wall section in the uncracked situation, or the wall partly cracked or fully cracked. So, depending on the condition in the wall, the crack condition in the wall, and depending on the mode of failure, you have a set of expressions which have been derived with the assumption of a parabolic deflected shape. For the column, you get the bearing capacity and the eccentricity corresponding to the capacity estimate itself. So, this is another format in which the effect of end rotations has been considered. If you actually look at the kind of rotation that you have of the slab with respect to the rotations in the wall at the interface between the wall and the joint, it is instructive to see that the total rotation is affected by how much rotation the slab is going to undergo and how much rotation the wall is going to undergo. So, there is this set of interesting this is an interesting work that has been done to arrive at moment rotation relationships for the joint behavior at the wall slab interface. So, if you are assuming that the joint is rigid, if you are assuming that this wall slab interface is rigid, you are going to basically have a situation where you are assuming that the wall's end rotation and the slab's end rotation are similar, but this is not going to be the case. you are looking at materials which are definitely of different stiffnesses, and these two values will not be the same. So, is it possible to make an estimate of these two, and if so, can a moment rotation relationship for the joint behavior be developed, and can that be used for your end rotation estimates, and then use it within a within those example parametric curves that we were looking at to estimate what the vertical load carrying capacity of the wall is going to be. So, this angle of rotation at failure depends on a few factors. It is how much of axial load is actually coming onto the joint, that is what is the axial stress level in the joint, and also what is this load in relation to the load carrying capacity of the wall itself. So, this angle of rotation is going to be different at different stages of the loading itself. So, if you look at the joint, this is basically examining a wall with a slab and the interface between the wall and the slab. Here the rotation of the wall is phi v, that is the rotation of the wall, the vertical component, the vertical element has a rotation phi v. The slab itself undergoes a rotation phi h. Now, the difference between phi h and phi v is really the rotation of the rotation of the joint itself, right. So, there is an estimate of the joint rotation that is now dependent on how much is the slab rotating, how much is the wall rotating, and the difference is going to give you the joint rotation. So, some work that has been carried out in the past has looked at an elastic plastic behavior where the rotation of the wall is assumed to have a nonlinear behavior, whereas the with load, with increasing load, the rotation of the wall is not linear, whereas the rotation of the slab is considered to be linear, and this is an acceptable assumption if you are looking at brick masonry and reinforced concrete as the two materials. I am assuming that the reinforced concrete material is continuing to behave in a linear elastic manner, whereas the wall has inelasticity coming in, and so the rotations are non-linear, and that is a fairly good assumption. So, in this graph you can see with increasing P on the y axis you have the different rotations, the rotation of the wall, the rotation of the slab, and the difference theta. So, you can make an estimate of what theta is once the total rotation of the slab and the rotation of the wall is made. And as we were talking, as we were discussing earlier, in the case of the reinforced concrete slab, if the pre-compression at that joint is about 0.3 MPa or greater, you can assume that you do not get rotations there, and it is a fixed joint, and this has actually been seen quite clearly in experimental results, that you get almost 80% fixity if you are looking at a compression stress level of about 0.3 MPa. So, with this you will have an estimate of the rotation, and then you can go use curves which are actually accounting for end rotations as well to be able to estimate the vertical load carrying capacity of a wall. Just to show you the behavior of such interfaces, if you have very low level of pre-compression in the wall, let us say you are looking at a single storied structure and the roof slab of a single storied structure. In reinforced concrete with low pre-compression levels, you will have fracture crack formation as as the wall starts deforming, whereas if you have high pre-compression, then the interface can see situations where there is crushing occurring in the brick masonry. These are of course outcomes of test, and what you are seeing is at failure conditions. So, the point is that interface will behave differently with respect to the level of pre-compression. It can either crack, or it can crack and rotate, or crush, and therefore, if it is crushing, then you have the non-linear behavior of the masonry wall. The rotations in the masonry wall will be different, and you cannot assume a linear response there. So, this is just to, so that brings us to the end of examining masonry under compression. We did it at two levels. We did it at the masonry cross section level, material compression, and the element compressive behavior itself. We continue examining different actions. The next that we will be examining is bending, but out of plane bending. And when we examine out of plane bending, we did discuss this aspect at the beginning of our section, in the section on material behavior, and how the strength of the joint in flexural tension becomes important. If you remember, we examined flexural tensile strength normal to the bed joint and flexural tensile strength parallel to the bed joint. Now, time has come when we start examining the role played by those parameters and the orthogonal strength ratio that I mentioned to you earlier in the behavior of the masonry wall in bending. Okay. Now, assuming we are looking at the wall subjected to horizontal distributed loading. So, now the load is actually acting laterally on the wall, and we can examine typically distributed conditions because we are interested in looking at the behavior of the masonry wall when subjected to either inertial forces generated due to an earthquake, and that is distributed load. Of course, we can idealize it as a concentrated force when we do seismic analysis, but basically the inertial force is a distributed force, or wind forces, air pressure on a wall. So, we are examining a situation where the wall is subjected to horizontal distributed loading, and this is in the presence of gravity load. So, we are examining a combination of loads here. The gravity load is present, the stresses due to gravity loads are already present in the wall, but in addition we have the lateral load acting on the wall. So, before we examine the analysis approaches to consider different situations, it is useful to recollect that we talked of horizontal bending and vertical bending, and you have situations where you have a combination of horizontal bending and vertical bending. We refer to that as diagonal bending, and that is again a case that we will examine. And horizontal bending and vertical bending is a differentiation that we make based on the predominant direction in which the bending is occurring, and that is dictated by the boundary conditions. So, both horizontal bending and vertical bending are referred to as one-way bending, because you have the predominant bending only in about one axis, whereas in diagonal bending you will have two axes about which the bending is occurring, and that is why we refer to it as diagonal bending. So, one-way vertical bending, you have again the situation that I am looking at is with rotations at the top and the bottom being possible, and then you see that there is a crack that is formed at the mid height, roughly at the mid height. So, these are some assumptions that the top and the bottom are free to rotate, and you get a mid height crack also forming. We will examine under what conditions these are true, but in most situations when you are looking at distributed load acting on the wall, lateral load acting on the wall, this is the way in which the wall is expected to respond. So, this is one way vertical bending with a mid height crack at the crack somewhere at mid height. It can actually be at other locations away from the mid height due to specific conditions, and we will examine that again. So, the maximum displacement could be delta acting because of the deformation of the wall itself. The question is there horizontal bending happening here? No, there is no horizontal bending. When we talk of one way vertical bending, it is about the vertical axis that the bending is happening, and you are getting cracking, the resistance is is offered by a joint and the flexural tensile strength of the material, normal to the bed joint becomes critical in one way vertical bending. When I am talking of one way horizontal bending, it is the wall which is actually opening inwards or outwards with a vertical crack that is formed, whereas in the one way horizontal bending you get a horizontal crack. That the orientation of the crack might mislead you to get confused with the title. One way vertical bending is bending about the vertical axis, one way horizontal bending is bending about the horizontal axis. The one way vertical bending ends up with a horizontal crack, the one way horizontal bending ends up with a vertical crack. So that is the fundamental difference. Okay. So your question is, what we are seeing is the wall being loaded in the axial direction. Now we are talking of a wall which is carrying gravity forces, but is also subjected to lateral loading, and the lateral loading that we are examining in this case is either wind load or inertial load because of an earthquake. So in this condition you have the horizontal load and deflections occurring in the wall because of the combination of the two. So you would have a similar situation in one way horizontal bending. Now the point that we need to make is that in one way vertical bending you do have the effect of precompression, the positive effect of precompression on the resistance of the wall itself. So if you are looking at a wall which has significant precompression, then its out of plane capacity, vertical bending capacity is going to be enhanced because of the presence of the precompression, right, and that is obvious because the precompression is going to act on the resistance side. What about a horizontal bending situation? In one way horizontal bending, can there be a beneficial effect of precompression? If precompression is there, it will definitely have a beneficial effect, but would you get the beneficial effect of precompression at all in horizontal bending? So that is something that we will examine. Do you think you can encounter that sort of a situation? We know the beneficial effect of compression, precompression, it is available in one way vertical bending, but what about in one way horizontal bending? Yes. So it is available if you have non-moving end supports, and if there is no gap between the wall and those supports, and if you have basically non-moving supports, the end constraints can induce precompression as the wall starts deforming. As the wall starts deforming, you will get clamping forces coming in, and those clamping forces will augment the out of plane capacity of the wall. It is called an arching action, and we will examine how one way horizontal bending estimates can be completely different if you consider arching action and the conditions are available for arching action to occur. So and that is the reason why I put this here, because while in one case it is obvious, in the other case it is not obvious, and it needs to be accounted for if conditions are available for it to occur.